Okay, so what we were doing, 360 says just worry about calculating the moment due to the force in this member BG. So we've got this cable that's tensioned up to 450, and that's why I have that portion of the problem up there. But we're not going to be looking at what BD does. So it's creating, there's a force now that's not along that line there that's going to create some moment about that line AD. And our first approach, what we're doing and what we started off with, was solving for a moment somewhere on that line. So we've got solved, and what we did on Thursday was solve for the moment using our cross product approach for the moment at A. Now what we want to do is project that onto AD. Okay, so what we solved for on Thursday, at the end of Thursday, was our moment at A. And we found it had a component in the J direction and a component in the Z direction. So we had a J and a K component there. Our next step is that we want to project it now onto this line AD. And the way we do that is we're going to need a unit vector now in that direction AD. So we're going to do the same sort of thing that we did before there. We're just going to go ahead and calculate a vector AD. And we'll note in the I direction there that D is down there at 1. 0.5 and 0.5 meter there is 1. So x of D is going to be 1. X of A is going to be 0. Now note that it lies on the plane of x and z, so there's not going to be any j component there. And then finally, the k component, sure I've got that right. Oh, minus. The k component then, z of d will be 0, z of a will be 0.75.
But isn't it positive 0.75?
And this is always subtracting though, remember? It's xd minus xa. It's always the difference. Good question, though. Make sure you're comfortable with that. OK. So we just simply create that vector. And then the next step we're going to do then is create the, we need to calculate the magnitude of that, divide by that, and we'll end up with our unit vector. And what we find then is the magnitude is going to be 1.25. And when we get done with that, we end up having our unit vector at 0.8 of I and 0.6. And again, if we take those numbers, square them, add them together, it should be it should equal to 1. Now we've got our line AD, we've got our unit vector in that line AD. We're going to now use our product, our dot product approach to project the moment that we calculated at A onto this line AD. So mathematically, what we're going to be doing is taking this vector times that vector. But we're going to use the dot product approach, which says then I'm going to take all the x components, multiply them together, take all the y components, all the z components, multiply them together, and then add them together. And if we go through and look at it, there's no x component for A, so that's 0 multiplied times our 0.8. We have 80 in the j direction, but we don't have any component in the j direction there in terms of my unit vector AD. And then the only other piece is going to be my 185. And what did I do with that? Oh, the 80. Yeah, the 185 and the 0.6. Which again is a scalar. So we come up with a minus value. What does the minus value mean? Opposite direction. So we're going to take our right-hand rule, we'll take our thumb and point it in the direction AD. And basically what it's saying is now it's going to be opposite of the curl of my fingers. The twist will be in the opposite sense there. So my AD will look like, let's see, do I got my picture there? And the twist is going to be that direction. You think about it, when we look at that piece of pipe there, it's going to want to pull it around that direction there. So that's going to be opposite direction in terms of a positive convention using our right-hand rule. Now, if I want the vector, basically all I have to do is just simply take this scalar value that I just solved for that times that unit vector AD. So what we're doing here is just simply expressing that same moment that we calculated, that 111, in terms of the component about the x direction and the component about the z direction there. And the signs then also tell us then in terms of x, it's going to be twisting in an opposite sense of the x there. So we put our thumb in the direction of the positive x-axis. The twist will be in the opposite sense there. Different for the z. Z basically will be saying it's going to be in a positive convention. OK, so that was our first approach. What we did was did a two-step process to get there. We took and calculated a moment at A, a point somewhere on that line AD. And then we then projected it using the dot product to get us to this value here of minus 11. And then if we wanted the vector, we could go on and do the extension. The second approach is a nice one in the sense that if all we want is that moment AD, we don't care about the moment at A, we don't necessarily want to go through that two-step process, we can do that approach there, the mixed triple product, which is just simply solving for a determinant that looks like this. So all we're going to be doing is then just solving a determinant. The only thing we do different here with this looks like the moment equation, except with our moment cross product, we had I, J, and K up here, those unit vectors in the Cartesian coordinate system there. What we substitute here for this mixed triple product is the cosines, the direction cosines of this vector AD. Question?
Is that last one supposed to be ADV?
Yeah. Thanks. I haven't had enough coffee yet today. So basically, it's just solving that determinant. It skips the steps, basically, of solving the moment if we lay it out like so. And again, you'll see the value of picking very easy directions there. Lots of zeros. If we can put zeros in here, it basically will save us a lot of work and potential mistakes. So our determinant will look like so. And then we start looking at what we're going to be crossing into. My 0.8 will hit a 0, so it's not going to do anything. Going the other direction, it's going to hit a 0. Nothing there. There's 0 in this direction both ways. And then the 0.6, and that's a minus 0.6. Is that right? Yes. OK, so the minus 0.6 will hit the minus or the positive 0.5, and then the 370. And then going the other direction, it hits a 0 there. So basically, I'm all done. So in terms of doing, say, for example, your EIT exams or something like that, if you've been asked to solve for it in a direction, you haven't been asked to solve for the moment anywhere or something like that, this is a much quicker way of getting there. And it also checks you. It's another check. So you can do the moment at A, do the dot product, and then check yourself against doing the mixed triple scalar product.
How do you do that again?
It's solving the determinant of a 3 by 3. So your choice of however you want to do it. I usually do it with the 3 by 3, but you can do it via the subdeterminants. Zero's there. Well, that'll be 0.
I mean, how do you, like, where do you multiply to when you do that? Where do you multiply?
Well, we go this direction, right, first, which is a 0, and then we go the other direction, which would be picking up that 0 for this top one. And then you move to this one. Well, that's going to be 0 anyway. Then this one will pick up that and that. And then it goes back this way. The minus track will be that way. I've posted it on the website. Go look at the handouts and stuff, and it'll show you how to do that. So it's just a way of keeping track of it. If you're not comfortable doing it, determinant.
No, it looks much easier. I'm not really sure where you're going when you look.
I'm making you dizzy, huh? Yeah. Yeah, it's we can talk about that after class. But basically, however you're comfortable, it's solving this determinant, a 3 by 3 determinant.
Yeah.
There's about 3 or 4 different ways of solving that. Sir?
Wouldn't the 3 by 3 determinant not give you a scalar? It would give you a vector in that direction?
No, because these end up being,
Values are not IJK?
these are no longer I, J, and K. Yeah, they're direction cosines. So before, when we did it as a cross product, they had direction because it was I, J, and K. Good question, though. But now they're just simply direction cosines. So they're kind of pointing out there somewhere in space based upon a coordinate system that we set up. Sir?
This is to find the moment.
We use this to find, this particular approach is used to find the moment about a line. And that line is defined on that first line there by the direction cosines, right? So good question. Think about that. We use the cross product, though, for finding, we did that earlier for finding moment at A. We did that on Thursday. And that's basically will find us the moment in terms of the I, J, and K components, like you like to see it. So if you need to find the moment in terms of those components, do it that way. If you're asked, and basically this is a way of checking yourself, or if you're doing, say, for example, an EIT exam, it's a much faster way of getting to a moment on a line. Very quick way. So have I lost everybody? So it'll be something fun you can play. Try it at home. You have homework problems. And now we'll get into today's subject. And if you do have questions on solving the determinant, I'll stay after class and we can kind of go through it. Okay, so what we're going to do is extend our knowledge of moments now by looking at this strange thing called a couple. And it's basically a moment produced by two equal, opposite, and non-collinear forces. Now, what was collinear? On the same line. So now we're saying we're looking at two equal and opposite forces, but they're not on the same line. So let's consider a couple of forces. Top one will be F, the bottom one will be minus F. Okay, so we got a couple of forces here that are going to be equal in magnitude, so they're both F. Opposite in direction, we have the minus sign in front of the 1, so it's saying I'm going in the opposite direction there. And I'll set up a coordinate system such that my x direction is parallel to those lines of action. And I'll consider a point, just somewhere down here we'll call O. And I'm going to measure some distances here. And I'll have a perpendicular distance to that first one that we'll call A. And then we'll continue that with a perpendicular distance D to the other F. Okay, let's consider the sum of the forces in the x direction. What are they equal to? Oh, you still drawing? Everybody's intently drawing here. I'll let you finish your pretty picture. But think about it. Now, if I want to sum up my forces in the x direction, I've got a positive F and a negative F. It'll be 0. So it's not going anywhere. It's not moving the body in any sort of direction there. Let's consider the moment now. Moment at O. Well, we'll consider the first force there. Now, we'll choose a convention. I always like doing this. We'll choose that right-hand rule as a positive convention there. So let's think about that first F there. How far away is it from O, perpendicular distance? A plus D, sure. Now, per my convention, is it positive or negative? It'll be negative. But it's the positive force. Does that make sense? different convention. Remember, rotation is going to be a completely different convention. So it's a minus, even though the force is plus according to my Cartesian system that I've set up there. Let's look at the other force then. I've got the other force, F. It's now only A away, positive or negative. OK. So note that we got an A here with a minus sign in front of it. And I've got an A here, so those are going to cancel. What I get for a moment of that is just simply F times the distance between them. And of course, the rotation will be this way, or another way of expressing that is a minus FD times the unit vector k. The minus sign then indicating it's going to want to twist me in an opposite sense. So my z direction's this way. It's going to want to twist me in that opposite sense. Now, one important note, the moment doesn't depend on that A. Oh, question?
So what you have written is not according to that picture then, because you have that bar right on that one. You don't need with it. Not negative.
I don't get your question. What are you saying? Yeah?
On your picture over there, you have negative F being closer to the moment O.
OK, I'm glad you brought that up, because this is the trick. Moments are based upon rotation, right? So it doesn't matter which way the force is going. We have to concern ourselves with the rotation. So if I'm at O, and I'm looking at this force here, right? My positive convention for z is going to be this direction. I've shown it there. This is why I always like showing this, because I'm saying that's my positive twist direction. When I look at this force in O, if I were to hold this at O, that force is going to twist me opposite. So it's a really important point, because people miss this all the time. The coordinate system, the positives and negatives for moments are different than what we're going to see here. It's a different convention, so we have to pay attention. We have to think, OK, it's rotating me this way. It's going to be negative. So a very, very good question. And I did that on purpose, because a lot of people say, well, oh, that's the minus F.
I meant because you have negative F at A plus D, and then you have F at just A.
Yeah, so F at A, but it's twisting positive. F positive, that positive by that convention, but it's twisting me in a negative sense. We'll talk after class. So it's a different convention. I do that on purpose because I want you to see the fact that we've got a convention for forces that are going to be linear, and then we've got a convention then for twists or rotations that are going to be separate.
So the sign of the force has no reference to the sign of the moment then, because it's just the direction in which it's being rotated?
Yeah, go back and look at, remember the little 2D moments that we were doing there with the little square plates? Go look at that, the very last one, the Varigon theorem. And one's twisting one way, the other's twisting the other direction. And it's based upon which way am I twisting. So you've got to be very careful of it. They're both positive forces on that example, but one's twisting negative, one's twisting positive. So take a peek at that. That's a really good point, though, because a lot of people mess up there. But the key thing is that M, this moment at O, doesn't depend upon where it is. So it can be anywhere on or off a body. We haven't even talked about the size of a body here, a rigid body or anything like that, basically. But the key thing is that this set of forces that is known as a couple there creates a moment then that basically is the same anywhere. I can measure it up here. I can measure it over here. However, it's only dependent upon this distance between the two forces. There's no free lunches, but there are free vectors. It is known in the convention of the statics basically as a free vector. And what that means is that it doesn't make a whole lot of sense here, but when we get into equilibrium, when we start adding pieces in terms of moment equations, it's just going to be a number that we plug in there. We don't have to worry about calculating or anything like that. And just restate that the direction and magnitude is the same everywhere. Okay, in the general case, when we just consider using our vector algebra, what we're getting comfortable with here slowly but surely, okay, so we again have a set of parallel lines of action there, and I'm going to draw them in the opposite order there. And we're going to pick a point somewhere else. I need to extend this line a little bit. So point O will be here. And then I'm going to draw a position vector in space, so it'll be having I, j, and k components to somewhere on that first line there. I'll draw another r basically between the two. And then finally, I'll connect it up with another position vector from O to, we'll call this point A. So this will be point A and point B. But basically, we've defined a triangle in space. And just recalling our parallelogram law, so that long arm basically is just going to be simply equal to that RB and R. Again, think about moving that book around. To get to this point here, I can go via RA, or I can go by the two-step process of RB to R. We can express this as so we're just moving it around a little bit. So what I'm going to do is create a moment, basically, of we're going to steal all of my important information. OK, so I'm going to do my moments here. I'm going to take a moment. Now, remember, via the approach that we did in 3D there, I can just take it to any point along that line of action there. So my first component will be taking that RA times that F. Now, in 3D, it's going to be important that I keep the signs in this case. So that's going to be a minus F. Now, by the associative law, I can then note that the fact that they're going to be the same F, oops, I can rewrite it like that. It's the same magnitude F, basically. It's the same direction, just the sign is different. So its sense is different. But notice that that's the same thing as that. Which again implies that it's going to be the same everywhere. It doesn't matter where I choose that point O. It's only dependent upon that distance between the two. And one additional thing to recall, let's see, you can get a different color here. So what we're saying then is that the calculation for this moment, even in space now, is just simply dependent upon this r. Remember the r and the f remember the magnitude we defined when we did the cross product was simply that r, magnitude of r times the magnitude of f times the sine of the angle between those. Well, if we think about it, that's that same angle there. What that's simply giving us then is what we kind of knew all along, is just that perpendicular distance. So the cross product, again, will correct us, take care of those angles and stuff, and make sure that basically the magnitude of that moment is simply going to be the magnitude of the force times that perpendicular distance between the two. Okay, so this is all kind of theoretical. We're gonna look a little at some equivalent, and then we're going to see what we're going to do with this. So the first thing we need to just think about is equivalent couples. So basically, equivalent couples means it's going to be the same magnitude and same direction. It's the same vector, essentially. A couple is a vector. It's a moment. OK, we'll look at a couple of cases in the same plane. Different directions. Okay, so we got a set of forces there, one acting vertically down of 10, one acting vertically up of 10. The magnitude of that moment is just simply going to be 20. F times d. An equivalent moment, we can change the directions, basically. And again, the key thing is their magnitudes are 20, and the rotation's in the same direction. So think about like a satellite in space there. When they're having to adjust it, they're twisting it. Doesn't matter which way the thrusters are going. If they're equal and opposite, basically, it's going to cause the twist in one direction, no matter whether they're shooting horizontal or they're shooting vertical. So it creates the same couple, and that's all in the same plane. And again, to be equivalent, the key thing is that it's not only the magnitude, but it has to be the direction too. So basically, the vector has to be the same. So that's different directions. The other possibility is using that same one, but considering we can use different magnitudes of force, but if we do that, then it's going to have to be a different distance. But again, it's an equivalent couple. It's the same. It'll cause the same twist on my body, considering out, externally how I'm holding it. Either one of these is going to do the same sort of twist to my body. We can also do the same, create equivalent couples by putting it on different planes. So what I have there is a little box. But I can set a set of forces up here. My pen to draw, right? And I can set it up that way on different planes. Again, when I'm thinking of a rigid body now, we're looking at more than a particle. It's going to be a engineering baked potato, or in this particular case, some sort of a rectangular box. But again, it creates the same twist whether I place it here or I place it here. So we have all of these cases then. We can create these equivalent external forces on a body. And just a couple of additional things we need to think about. They are vectors, which means then we can do vector addition on them. So I got a set of forces up here on the top. F1s, one's acting one direction, the other's acting the other direction, separated by a perpendicular distance of d1. I can have another set of vectors, or forces, my F2s, that are separated now by some perpendicular distance d2. We can express that as a vector moment. I use the double arrow to indicate that it's a moment vector. So it's talking about twist, if you want to add twist there, but think about it, it'll be twisting this way. The set of forces 2 will do the same sort of thing. There'll be a twist. Oop, and I forgot my extra arrow there. About that bottom one. And again, remember those moment vectors. The vectors are perpendicular to the plane created by those forces. So if they're in this plane, it'll be pointing directly out. If it's on that plane, it'll be perpendicular to that plane there. So I can take those. They all end up at the same point there, in the middle of the box there. But what I can do then is simply project that onto add it. Yeah, let's not put those there. We can just simply add them together, basically. A little harder to see it that way. I can just add them like we do force vectors. Take the x components, add them together, the y components, again, paying attention to sign. But basically what I can end up with then is one vector, basically, that describes what these two sets of forces are doing. So it adds just like the force vectors that we're familiar with in terms of 3D forces. We use our same tools. The other thing is that we can actually decompose them to, where's my blue? Okay, so we might have a moment vector such as that one described there, caused by those couples. But we can break that up then into a So we can break it up just like we do with a resultant force. There's going to be an x component, a y component, and a z component. So we can basically describe it in terms of our direction cosines or just the components. And what we'll find is that we'll be doing the same thing we did with the forces. We can use direction cosines. We can use the two angles if we need to find it that way. And the most common one basically is what we've been doing is the 2 points. Find a point over here, find a point over there, do the x2 minus x1, y2 minus y1, and that sort of thing. But it behaves just like a vector. And we'll be treating it like a vector. Oh, question, sorry.
No, I'm just going to say, what's the double arrow? Is that only you do that for moments?
I do that with moments just to indicate it's a twist, not a force going in that direction. So I just kind of do that to make it clear. But good question. Yeah, I do. I have my little shorthand things that I do to make things clearer for folks.
Is that the direction of the twist, or is that the axis that it twists about?
I beg your pardon?
Is the arrow pointing where the twisting is going, or the
Yes. Yes. So when we think about it, what this arrow is indicating, this M, is maybe it's a whole bunch of forces and everything creating a twist about that direction. So I put it in that. Positive, it goes this way. Negative, it goes that way. But I can break it up because it's a vector. I can pick, one of these methods to figure out which way, to create my direction cosines. And then I can break it up into an x component, a y component, a z component. The reason why we're going to want to do that is when we get into equilibrium, we're going to start adding pieces up and that sort of thing. We want the scalar equations. We want to get down to mx, my, and mz. That's where we're going with it. That answer your question?
I was just forgot about the positive and negative.
Yeah. Again, moments, a whole different convention. It's twist. So you got to think about it, and that's why we use the right-hand rule. Just take your thumb and point it in the positive sense of x, y, or z, or whatever, and then your sense will be basically based upon the curl. If it goes with the curl of your fingers, it's positive. Opposite, it's negative. OK, so where we're going with this and it seems kind of funny. It doesn't seem like a reduction. We're going to take a force and we're going to create two things out of it. So we're going to take a force and we're going to create a force couple system. But again, this is showing us how we can basically put it together, and this is leading us towards our equilibrium. OK, so we'll put up the engineering baked potato. There'll be a couple of points here of interest. We'll have an A and a B. And then, for example, we'll have some sort of spring that's we'll have a spring there that's going to be having some force in it created by the fact that we're going to have this force at B along this line of action there. So at B, there's going to be some sort of force. We're going to end up with a spring force in there to keep it in place and that sort of thing. Where we're going with this supposed reduction is what we want to do is move everything to A. For example, maybe I've got a support at A. And I want to know, OK, I've got this force here caused by something else, a wire attached to it. And I'm at A. I need to find out what I need to do in terms of getting A to support that. What sort of forces am I going to need to resist? What sort of moments am I going to need to resist? So what's going on there at A? Well, what we do is we find that we can create an equivalent system. That's the 3. OK, so going back, I've got my force there. What I'm going to do is take an equivalent line of action, or parallel line of action. So I'm going to draw a parallel line of action. What I'm going to do is I'm going to put a force F there, and also put a minus force F there. So what does that do to A, that set of forces?
Cancels out.
Nothing out, it cancels, okay? But, oh, and the other thing we'll do is note that there's going to be some perpendicular distance between those two lines of action. They're parallel lines of action, so there'll be a perpendicular distance there. Okay, so that's not doing anything at A there, but note, does this force and this force look like something we just got done talking about?
Yeah.
Come on, don't all say it at once. Okay, we can take that and create, now notice that F will be left, but then there'll be some sort of twist. I don't know, that's moment at A. What I can do is replace these two forces with a couple, that thing that I just created, which is now a vector. But now I've got everything at A. So if I'm designing, like, again, a support or something there, then I know what I need to design there. And the other key thing is that my spring force is equal in all those cases. And again, that goes back to my rigid body thing. As long as everything's happening, I'm supporting it on the outside with some sort of a spring there, each one of these systems basically says the same thing, does the same sort of force in that spring force. And we'll identify this body as 2 and this body as 1. And then make a whole bunch of notes here. Okay, so 1 and 2, as we said, are equivalent force systems. They're going to create the same question.
Yeah, but wouldn't those different forces cause different rotations? The diagram 2 would cause a rotation to the right.
Well, let's think about that. Yeah, okay, so I'm going to hold it at A. All right? I got this force here. Well, the force is going to want to drag me in that direction, right? Yeah. And it's also going to want to twist me this way, right? Now let's go here. Going to want to do in the same direction, and the twist is the same direction there.
Are you going to be holding on to A or B?
Holding on to A.
Well, if you're holding on to A, the force is connected to that point, though.
It's on the same LOA.
But it's on the same LOA, so it's going to move my body in the same line of action. And the twist is going to be the same amount of twist because it's F times D that this one's going to do. See it? Okay, yeah, think about it. We'll talk about it after class. Sir?
You were just writing the MA instead of putting more forces on it.
What I did was I took the forces. I took these two forces and created a couple with them. F times D, right? That's what that moment is. So there's going to be a moment, a vector sticking out like this that says I'm twisting you this way. But it's creating the same thing if I were to hold this one at A and allow that force to do it. The force is going to want to make me go this way, and it's also going to want to twist me about A that way. This same force system does the same thing at A. Wants me, drag me in that line of action there, and it's going to want to twist me in that sense. And the same amount, because MA is basically going to be F times D. If you believe that, I got a car I want to sell you too. So think about it. we'll go through some notes here. Maybe some of these notes will help you clear up. Okay, now another interesting point is notice that force at A is the same force as B. It hasn't changed. Same line of action, same magnitude, going the same way. Okay, so MA is then going to be perpendicular. In this particular case, since D and F are in the same plane there, the plane of the board there, basically my moment vector is going to be in the Z direction coming in out of the board. Okay, MA is a free vector. That'll make a little more sense when we start adding things together and all. And the important point we just kind of talked about there is that external spring force is going to be the same for either one of those cases. So externally, my body doesn't care whether the force looks like this or the force looks like this. Now, like I said, that didn't make a whole lot of sense. We resolved a single force into two force in a moment or a force in a couple. But we can actually reduce it into a single force. We'll go back to our body at A there. Okay, so our point 2 there, when we were done with that, we ended up with a force and a twist about A there. Now what I want to do, and what I'm going to do, and I can do this in 2D, you can do it in certain cases in 3D, but basically I can get rid of that moment by just simply moving my force down some distance d. So if I take my point A, I can move that force, keeping the same line of action, but I can take that force and move it some perpendicular distance d away, and d we can recall, moment is going to be F times d, the magnitude of the F times d, so we can also set that up as solve for d. But again, the key thing here is I can now take this force couple system and just simply move that force a perpendicular distance calculated by the moment there, and it does the same external effect there that I would have on this one. Question?
Why did it become negative?
Oh, sorry, that's a smudge. Because Dr. Holland had it on his fingers, I think. He has negative fingers. But again, the key thing is that it's, in terms of the spring force, this external force here, I've got a couple and a force. The force is wanting to drag me this way, and it's wanting to twist me this way. Same thing with this one. If I'm holding it at A here, it's going to want to drag me in this sense, and it's going to want to twist me in that sense. So I can reduce it down to, and this will be some of your homework problems here, is going to be reducing it basically to that, moving that force to some point of line of action. Matter of fact, that leads us right into our next problem here.
So is that essentially just the last thing, but in reverse?
Yeah, we're just kind of going backwards now. But you're going to be doing this with multiple forces. So we've demonstrated with one force, which, you know, kind of like, wow, what's exciting about that? When we start doing it with multiple forces, then it'll become a rather interesting problem. So we'll let you finish up your notes there, and we'll look at the handout problem. If you don't have the handout, come up and grab it. Smudgy. Okay, so your handout, I've done a little pre-work for you there, but basically what we've got is a set of forces there that kind of looks like a couple. The Q at A, and it's 40 pounds. One's acting one direction, the other's acting the other direction. Then we got this extra force there, P, which is 60 pounds at an angle of 50 degrees. And I think I've got your px and your py components. Are they calculated for you already? So we just basically got that out of the way. We've got x and y components there. And we've been asked in two parts there to take and give replace the force and couple with a single force at along line AB and then one along AC. So what we're going to see is we're going to have to do that two-step process. We're going to have to create a force couple system at one point. We got three forces here. So we're going to have to bring them all together. It's not that single force anymore there. So we're going to have to create a force couple system at some point. Now, what point should we do? Well, since we have to do it along AB and AC, A makes the most sense because that lies on both lines there. And that'll give us the ability then to do that projection that we just talked about there in a perpendicular distance there along A, or a perpendicular distance along AC there. Okay, so the first step we'll do is we'll move that minus Q to point A there. So we'll be looking along this edge AC. And already at A, we've got a Q going in that direction there. And what do we have? A distance there of 25 inches. Okay, so per what we just did there, what I'm going to do is take this q and I'm going to add another q there and another minus q. Okay? Now, with this set, I can take and create a couple. So just going through and doing the multiplication there, the distance there, QA, basically that's that 25 inches times the Q. And then we'll note that in terms of forces, oh, hold it, I grabbed the wrong one. What I want to do is grab the one that's going in the opposite sense there. Right? So this one's going this way, this one's going that way. So that's my couple. And then I want to add my forces there at A due to Q. And that's equal to 0, which kind of makes sense when you think about it. You know, a Q and a positive, it's already a couple. So we already know it's a couple. And the key thing is then we were able to calculate that vector as a minus 1,000 pound inches. Okay, so my next force, I'm going to move. I'm going to take, and the key thing here is I'm moving things to A. So when I move something out of its line of action, so I've taken this Q down here, and I move it up here to A, I create a couple. I don't need to move the Q up here because it's already going through it. There's no couple created by that. But anytime I take a force and move it to a point that takes it out of its line of action, you're going to get a couple. You're going to get moment. So we're going to have the same situation with P. Now what I want to do is basically take that P and move it to a P and a minus P like so. That 25 inches also, yes. Okay, but the difficulty is that 25 inches now is no longer the perpendicular distance, right? So a couple ways I can deal with this is, first of all, I could sit there and do some mathematics and do my inverse there of slope and stuff like that and come up with a perpendicular distance. Or, why I broke it up into x and y components, I can consider each component individually. So I have the py, and what I'm going to do is put a minus py here and a positive py here. And I'll take those two. And then the other piece I need to consider is those x components. So I've got the x component that I can treat separately. And I'm going to do the same thing. I'm just going to move px over here and have a minus px. Now, this one creates twist, right? Because there are two forces out of the line of action. All of these forces are collinear, right? So there's not going to be any twist there. But what we'll see is the component of fx is going to just simply be equal to px Okay, so what we see is the force is going to be the same. The x component and the y component are the same. The only difference is now in terms of the moment created by F, or P, is now only going to be this component in the y direction times that perpendicular distance of 25. And just simply going through the calculations now, the perpendicular component, py or fy basically, times that 25 is what's going to give me the twist. The horizontal component gives me force, but it doesn't give me any twist. Okay, so what we want to do is just simply add all these particular pieces together there. We've got multiple forces. Or we can express it in terms of I and j and k. So basically, there's no contribution from the q because it's a couple, a pure couple. And the only force that we'll see at A due to these sets of forces is just simply P moving over there. Now, what we'll have, though, by moving that out of its line of action, we're going to have the moment created by moving P out, but we're also going to have the moment created by Q, which is a pure couple, right? And this is where that free vector piece comes in. I just plugged that in. That's the Q piece. We calculated that earlier. Always useful to keep track of those units there and stuff like that. And when I get done with it, one's twisting one way, the other one's twisting the other direction there. And I end up with a resultant at that corner A of a force, which is basically P, and then the moment created by not only the force moving P out of its line of action, but also created by Q, which turned out to be just a pure couple. So we weren't adding any force in here due to Q. It's equal to 0. But we do have to include the moment there created by Q. So to solve for A and B, then, we're going to be asked to solve for an equivalent force along AB and along AC there. Okay, so what I've got at this point in time is an equivalent system there at A. Oh, question?
Yeah, so what happens to the x component of the P force then if it's in the same direction as Q?
It's right here. P, we just simply slid P over. So the x component's there,
yeah,
and the y component's there.
And then your P is adding to the moment caused by Q.
The component of, in the y direction, moving it over there to A created some moment, yeah, by simply shifting that over.
Yeah, and then there's the X component of that P force that's compounding with the Q component of the other force.
Yeah, but I'm at A here. P was applied over here, right? So the X component goes along that direction there. So I'm bringing it along in terms of force, but it's not creating any twist because there's no rotation. It's going through the point A. Does that make sense?
So then why is it the same force for the little circle body when we had the force put at point A and we were pulling on it? It's the same principle, right?
Yeah. So I've simply moved that force over. P's just simply moved over there. But the moment created by moving that over there is only dependent upon the y component, the perpendicular component, to get me over there. So the x component's there, but it's not causing twist. It's just brought along here, and that gives me that p in the 50-degree direction there. OK, so where we're going with that then, oops. Now, note, we talked about that. Are we getting close to the end there? OK, we'll finish up real quick here. Basically, anytime I move a force around, we keep the force, right? It doesn't change. So I'm moving P here. What I want, note, I've got a y component. And what we want in terms of A there is that perpendicular distance and the horizontal. And the way we do that is, again, we think about that perpendicular component. What I'm doing is I'm saying I'm creating an equivalent system here. The force is going to drag me along this line of action. Same thing here. That force drives me along the same line of action there. I have a twist now of 149. The way I create that twist by holding it at A there is moving that over such that the perpendicular component and the perpendicular distance are measured by ma, the moment at A, or that couple at A, divided by the y component, or the perpendicular component, in this direction of the force in that direction. Make sense? OK. Uh-oh. Question?
Next to D, what does that say? D what?
This H. Horizontal, because the other one's vertical. Different D's. I'll tell you what, on the back there is a three-dimensional problem there. I will post that on the handout section tonight. So you can take a look that your final homework problem is kind of like that. So it'll be a very similar thing to watch go through.